Okay, so we're up to the technology side of things, and it's been interesting that with the industry becoming such an important industry internationally, that it's been seen as being important that a team of experts from around the world be put together to try and assist the industry figure out where it's heading, what are the trends that are taking place, how are things likely to evolve. Now, this started off as a European initiative, which is probably sensible because that's where the dominant markets in the world have been in the past for photovoltaics. I'm pleased to say, though, that the team of experts shown here has been expanded very significantly, and they're now including quite a few others from around the world in their team of experts. So, for example, there's 5 of the largest companies now from Taiwan and China that are now represented in the team of people contributing. And so when you look at all the latest projections and predictions coming from the team of experts, I think they're actually becoming more and more relevant and more accurate because they're getting a better cross-section of feedback from all the biggest cell manufacturers and leading researchers from around the world in contributing to their roadmap. So it's called the International Technology Roadmap for Photovoltaics. And I've taken some extracts from that to basically lead you through a look at some of the trends that are taking place in the manufacturing and technology side of things. So this is a bit of a summary of some of the key areas. So silicon itself is always a very important area because silicon has in the past been the dominant cost of making photovoltaic modules. Now, you're probably all asking, well, why should that be the case? Silicon is dirt cheap, literally dirt cheap, because silicon is the second most abundant element in the Earth's crust. And so when you go to the beach and lie on the sand, I won't say it, Linda. When you do, yeah, you'll probably see Linda there. Yeah? No, that's not what my point was. My point is that lying on the sand, you're lying on silicon. Okay? Sand is just oxidized silicon. Silicon is basically everywhere. Okay? There's only oxygen that there's more of than silicon. So it should be really cheap, and it is. The problem is you've got to purify it. To make good solar cells, to make high efficiency solar cells, it's got to be good quality silicon. And what that means is high purity silicon, and also then when you crystallize it, you want very good crystallographic quality. So they're the two challenges. Purify it and then make it very good crystallographic quality. If you do that, you can make very high efficiency solar cells. This university has a very good reputation in that area, holding the world record for most of the last 30 years really, in terms of the world record for efficiency with silicon solar cells. But we always use the best quality silicon of the highest purity and the best crystallographic quality. Whereas when you get to a production situation, a very important issue is also how cheaply can you make it? How much can you bring down the price? And so all the cell manufacturers don't use silicon of the same quality that we use in our labs. And so it's very important that we can adapt our technologies to be able to work well with the much lower cost of silicon. And so Siemens' process has been the one that has dominated over the last 30 years as being the way of purifying silicon. It's a distillation process. It's a very expensive one because it's very energy intensive. And so that's been a big contributor to why purified silicon is so expensive. That's changing a bit now. There's alternative techniques that are being developed for purifying the silicon. Probably the best known one is what's called the Fluidized Bed Reactor. It's not a distillation process. It still uses chlorine to purify the silicon, and it is able to purify the silicon to nearly as high quality, but using much less energy, and therefore it's much cheaper. So that's one of the newer technologies around. There's also a lot of other companies that are trying to use even cruder approaches to purify the silicon, and we call them UMG processes. UMG, the U stands for upgraded, MG stands for metallurgical grade silicon. So metallurgical grade silicon is the basic silicon that's pretty low in purity, around about 98, 99%. And it's very cheap to get silicon at that sort of purity. but we probably want about 6 nines purity to make good solar cells. Now, you can use some fairly crude techniques to do that, to get that sort of purity, and there's quite a few companies around that we're working with that can produce 6 nines purity pretty cheaply, and we call it UMG silicon. Siemens' process, on the other hand, can give you 11 nines purity. The point is we don't need it. For most of the commercial cell technologies, you don't need 11 nines purity. A couple of companies have technology that does need much higher quality and higher purity silicon. They tend to be the ones that are making the very highest efficiencies, like SunPower, Sanyo. They have the highest efficiencies, but that's very much contributed to by the fact that they are using the very expensive, very high quality, very high purity silicon. I'm going to focus mainly on what 95% of the manufacturers are doing, and that is using the standard commercial grade silicon that is much, much cheaper. And so these are expected to be the two dominant processes going into the future, and the price of silicon has come down enormously. Then we have the wafers. So once you've got the silicon, you then need to turn them to the right crystallographic form. So you normally melt the silicon and then you crystallize it. There's a range of ways you can do that, and we're seeing some evolution in the techniques used for producing the silicon, techniques that are able to help bring down the cost. One of the things that's happening is that the thickness of the silicon wafers is being reduced. Obviously, if you make them thinner, you use less silicon, so the silicon's cheaper. Also, by making it thinner, you don't actually sacrifice any of your efficiency of the solar cell. The main problem is that by making it thinner, you can break them more easily. So the challenge is thrown to the manufacturers to still be able to try and make their solar cells with the same yields when the wafers are substantially thinner. And that's where the challenge lies. So the expectation is that the thickness of wafers will decrease from the present around about 180 to 200 microns down to about half that, 100 microns, over the next 10 years. And that will also help bring down the cost. Also, we see this evolution in the type of silicon. 70% in 10 years' time is still expected to be P-type silicon. There's been a lot of discussion on this because N-type silicon is usually considered capable of making higher efficiency solar cells, but it's more expensive to do so. So the expectation is that within 10 years, P-type silicon will still dominate probably about 70% of the market. And this new type of process involving the high-performance multicrystalline silicon is what is expected to dominate. I'll talk a little bit more about that shortly. Okay, then we get to the metal contacts, a very important part of making a solar cell. You need to extract the current from the solar cell. You need metal on the front and back with a conventional design. And looks like my laser pointer's dying. But anyway, at the moment, silver is predominantly used for the top metal contact. The trouble is, with the growth in photovoltaics, the industry is now using so much silver that it's contributing to pushing the price of silver up, aggravating the shortage of silver internationally. And so the price of silver has gone up very significantly. And so the experts have concluded that the industry has to become far less dependent on silver. And so there's the expectation over the next few years that people will figure out how to replace silver with copper. Copper has the same conductivity, so therefore it's a good alternative, but it's 1/10 the cost. So copper is a good thing to shift to. But people have to figure out how to be able to use copper. See, silver's easy. You can just grind it down into a powder, turn it into a, oh, beautiful, thank you, thanks Alison. Turn it into a paste and just screen print it. And there's been a lot of good development take place with screen printed technology. They're able to screen print the lines narrower and narrower with better and better conductivity, etc. So it's a good technology, it's doing well, and it's still dominating in manufacturing. But you can't do copper the same way for a range of reasons which I won't go into now. And so alternative techniques have to be developed for depositing the copper. And some great technologies being developed at this university and in conjunction with some of our industry partners to make it possible to do that. But it's not in widespread use within the industry at this point in time. However, it's being more and more recognised by the experts that copper as a technology has to be developed in terms of being able to apply it or deposit it onto the surface of solar cells to be able to replace silver. And it's expected that by 2017, copper will replace silver as the dominant metal being used in solar cell metallization. Now that's not far away. It's only 4 years. And there's a lot of work needs to be done on developing the technology. Everybody knows how to plate the copper. That's not so much the issue. But you have to be able to do so reliably and uniformly. You have to be able to do so that your metal contacts have the right adhesion onto the silicon and don't peel off and things like that. So there's a lot has to happen to prove the durability and viability of such technology. And so we have some big projects being managed by Alison here at the university, developing that type of technology for our industry partners. Okay, then we're also finding some evolution in contact formation on the back. So at the moment, just about all solar cells have metal right across the back contacting the silicon. That's not the best way of doing it in the longer term, but it is the cheapest way and the simplest way, and that's how it's done at the moment. But as we move to higher and higher efficiency solar cells, it's going to be important that companies replace that rear design with one that uses a dielectric layer right across the back surface to passivate the back surface. And then you still have to make contact to the silicon though. And so what you then do is you have to provide patterning of that dielectric layer, either holes or lines or circles, whatever you like, but you have to enable the metal at the back to penetrate through those openings in the dielectric to contact the silicon. It's not a trivial thing. And even when you figure out how to do it, you have to be able to do it in a manufacturable way. Very high throughput with high yield and at low cost. And that's where the challenge lies. We're starting to see the first companies now introducing that type of cell design. Probably the first company to announce something was Scientia 2 years ago, where they got over 20% efficiency with that type of cell design. But a couple of other companies have probably done a better job at actually getting it into large-scale manufacturing. And we're now seeing companies like REC, companies like Sunrise from Taiwan, REC's in Singapore. I think Qcells in Germany have introduced large-scale manufacturing of their technology with the dielectric at the back. I think Trina with their honey cell have got to pilot-scale manufacturing with that equivalent type of technology that's got the dielectric layer passivating the back. So it's a direction a lot of the companies need to head in, at least for some of their product, because the potential to increase your efficiencies is very significant. There's been a lot of good developments in recent years that I've talked about in previous lectures of this nature each year to do with the front surface. DuPont deserves a lot of credit. They've done a great job improving the metal paste, improving the techniques for applying the metal contacts to the front surface. It's enabled a big improvement in the emitter design at the top surface of the solar cell, the contacting mechanisms, the contact resistance is achievable, reduced shading losses, more lightly doped emitters that allow you to get better blue response and higher voltages. All of that has been happening in recent years, very much thanks to DuPont. And so the typical screen printed solar cell only a few years ago was limited to about 16.5%. It's now at about 18.5%. Some companies are getting up to 19%, and those that are starting to introduce the passivation at the back, they're jumping to over 20%. And that's really important because only 2 years ago, that team of experts that I talked about concluded that silicon solar cells in commercial manufacturing would never get over 20%. And it was going to take to 2020 to even get there to 20%, and that was the limit. And that was their predictions year after year. But as we find more and more of the Chinese and Taiwanese and Asian companies getting involved in that team of experts, the overall feeling is changing. And now we're seeing the predictions are no longer limited to 20%, they're now up to the 21 to 22%. Because quite a few companies are getting to the 20% now, or will be very soon in large-scale manufacturing. And there's still more room for improvement. And so we're going to keep seeing these improvements take place. 21 to 22, I think, is almost certainly achievable. And we believe that 23% is achievable with the standard P-type commercial Czochralski wafers that most manufacturers are using. So that's where it's all heading. So the experts are changing their attitude. Interestingly, Only 2 years ago, they had P-type limited to 20 and they had N-type up at 23. That's all changed. Now, they're not so optimistic about the N-type. N-type's now listed as 22 to 22.5, and we now have P-type at 21 to 22. So the experts are now thinking there's actually not going to be that big a difference between the two. And that agrees with our assessment. We don't see any reason whatsoever that P-type technology will not do just as well as N-type technology, but do so with significantly cheaper wafers and wafers of lower quality. So that will be very interesting to see how that pans out in the future as technology keeps evolving. And so these are the types of predictions now. And that is that here's the P-type that's boron doped. They're the P-type Tucholsky wafers, 21 to 22. The phosphorus doped, which are the N-type, still above 22 is what's predicted. Multi, which are a lower cost wafer, they're no longer a single crystal. They're the high performance multi that I was talking about. It's a lower cost but still quite good quality wafer, is expected now to get over 20% efficiency. Okay, and then we get to the modules themselves. I've already mentioned how there needs to be work done on the encapsulation. Those costs need to be brought down. There's going to be increased use of frameless modules because the frames are quite expensive. And there's no real reason that you need to use frames in a lot of applications. So we're going to see an increased use of these frameless modules, and we're going to see lower cost encapsulation techniques and materials being used, but hopefully without compromising quality at all. Okay, so let's just move briefly through those different areas. I've already talked about the silicon. We've got the two dominant processes, which is, here's the Siemens process, which at the moment is more than 80% of silicon. And then down here we've got the red, which is the Fluidized Bed Reactor. It's expected to become more and more popular because it's quite a bit cheaper, and yet its purity is quite good enough. And so it's going to increase in its use. The green triangles are the interesting part. That's the other areas, the lower cost, lower purity, lower quality silicon that we call the UMG silicon. And people are still trying to figure out where is that going to head. And so it's only at about 10% at the moment. And the team of experts at the moment are thinking, well, look, the other silicon is getting cheaper all the time. We don't really need the UMG silicon in the future. Now, maybe that's right. Maybe the high purity silicon will keep getting cheaper and there's no need to use UMG silicon. However, there are some new technologies being developed that look like they've got the potential to take the lower quality UMG silicon and provide a post-processing additional process to improve the quality of the silicon by using hydrogen to passivate. Now, hydrogen has been long known capable to passivate defects and contaminants in the silicon, but there's been some potentially some good breakthroughs in that area just over the last year or so, with some projects that this university is working on in conjunction with some of the big industry companies, some of the cell manufacturers. And it's too early yet to say how successful that will be, but if it continues to develop the way it looks like it may be able to do so, and if it turns out to be stable and durable, then there may be the option to use significantly cheaper silicon and apply this passivation technology to it to create a silicon wafer that is essentially as good in quality as these ones made from the more expensive silicon. So if that does happen, then this UMG silicon may in fact grow in its consumption in the future, but it's too early to tell at this stage. Okay, that then takes us through to looking at the wafers. I've talked a little bit about the wafers already, and what we see here is the dominant wafer at the moment is the conventional type of multicrystalline silicon wafer. And that wafer is actually expected to reduce right down. It's not because multicrystalline silicon is expected to disappear. They simply found a better way to produce the multicrystalline silicon. And this has been a rapidly evolving area. In the last 2 years, when I've talked about the casting process used for making multicrystalline silicon, I've talked a lot about this new technology called seeded casting. And what it is, it's still a casting process where you simply pour the molten silicon into a mould, let it cool slowly, and therefore it crystallises. But with seeded casting, what you do is you put a seed layer at the bottom to nucleate the growth of your crystals to try and cause the ingot to grow as a single crystal silicon. And there's been some success with it, but there's also been some problems with it. And one of the problems is the fact that as this ingot of silicon gradually crystallizes, you get a lot of stress accumulating within the silicon material because there's a change of density during the solidification process. Molten silicon has a different density to crystalline silicon. And so the growth process is involving this, not just the phase change, but the density change and an accumulation of stress in the silicon material. Now, one of the problems is if you're growing a single crystal, you just keep accumulating stress to the point where you start generating dislocations in the silicon. Those dislocations then propagate right through the whole rest of the ingot that you're growing. And by the time you get to the top, you have a very, very high density of defects to the point where that silicon is much, much lower in quality than the silicon that started at the bottom. So for a couple of years, we had all these reports from cell manufacturers saying what fabulous performance, fabulous efficiencies they were getting from their seeded cast material, but they were all using the material from the bottom of the ingot. No one was talking about the crap material from the top of the ingot. Right? Everybody thought they could solve it. And people have been trying to solve it and haven't succeeded. And so it's got to the point where people have started studying it saying, well, hang on, our normal cheap multicrystalline material starts with a lower quality, but by the top of the ingot actually has a better quality than the seeded cast material. So we must be doing something wrong. So they've gone to a different approach because what they've realised is that during a normal multicrystalline silicon ingot growth, you are still generating this stress within the silicon, but the stress relieves itself because you've got grain boundaries all over the place. And so if you get any defects forming, the defects simply propagate to the nearest grain boundary and extinguish themselves. So they don't propagate through the ingot. And so, provided you've got grain boundaries close enough, you can form an entire ingot, and when you get to the top of the ingot, you don't have any higher dislocation density than when you started. And so that's caused people to actually go in the opposite direction. Instead of trying to make one huge crystal out of the whole ingot, they've now gone in the other direction and they're deliberately making smaller crystals to avoid this whole problem of dislocations propagating through the entire ingot. Now, one of the problems of doing that is that you now increase the grain boundary area to even being higher than conventional multi-material. And when you do that, the problem is that impurities within your silicon, when the silicon is growing, most impurities that are nasty have a segregation coefficient that's very different to the silicon, much lower. Now what that means, I'm not going to go into a lot of detail, but as the silicon is growing, these impurities segregate out. They don't get incorporated into the solidifying silicon. So they stay in the molten region, but where you've got grain boundaries, you lose that ability to segregate. Okay, you segregate in the crystallizing regions. In the region behind it, it's a bit like an amorphous region. You lose the ability to segregate, so you get this collection of the impurities at the grain boundaries. So when you move to high performance multi, you're actually making grains, if anything, a little bit smaller than conventional multi, but you have to solve that problem of segregation of impurities to the grain boundaries. And so what they're doing is they're actually using a higher purity of silicon. Now I know that sounds like we're going in the wrong direction, but the cell manufacturers are looking at how the price of the high purity silicon is dropping and how cheap it's become, and they're saying it's not a problem anymore to use that silicon and therefore produce the high performance multi. Smaller grains, lots of grain boundaries, but ones which don't get the contaminants because we're using high purity silicon. Therefore, we make wafers that are the same quality throughout the entire ingot, no more non-uniformity like we used to get, and we've got a material that's not just uniform, but it's good in quality and able to make highly efficient solar cells. A lot of companies are now heading in that direction, and that's why the experts, when they look at it, they're jumping to the conclusion now that the high performance multi here, it's only 10% at the moment, but it's going to be the dominant wafer type by whatever date this goes up to, which is, what, 20... 23, whatever. Okay, so seeded cast material is no longer the flavour of the month. It's going to be dropping down very substantially, maybe not even used at all. There's still a couple of companies looking at it, but really it looks like this type of wafer may well dominate in the future. Now, if it does, that will make it hard for the UMG silicon producers, because people making the high-performance multi don't want the UMG silicon. There's too many impurities in there. And if you get all those impurities into the grain boundaries, it's very hard for the hydrogen to passivate contaminants and defects at the grain boundaries themselves. Okay, the hydrogen passivation technology seems to do a good job on the crystalline regions, but not necessarily a good job at contaminants that are located in the grain boundaries. Okay, moving on then to metal contacts. Again, I've talked about them somewhat with the evolution from silver to copper. These are the screen-printed silver contacts at the moment, almost at 100%. And yet that's expected to drop down to not much more than 20% by the end of this period here. On the other hand, here we have two types of copper-plated contacts. One of these is electroplated, the other is light-induced plated. But there's a couple of different plating techniques you can use for depositing the metal contacts. Both are expected to grow quite well. Both are expected to take over from silver by the end of this period. And actually, when you come back to 2017, which is only 4 years away, if you add these two together, in combination, they exceed the use of silver as a metallization approach for the solar cells. Other than that, that's probably all we need to look at there. Okay. So in looking at the copper, we do have, as I mentioned, some companies already looking at the use of copper-plated contacts. Here's a list of some companies that we know of, because we're working in conjunction with most of these. So Suntech, we've got a collaboration with IMEC involving plating of the contacts. Hyundai, Shinsung, UNSW, of course. RENA is a company that's developed their own plating technology. Schmidt's another one that's developed their own plating technology. So there are also other companies working on the plating side of things. This shows you the difference between two solar cells. This one's got the silver, this one's got the copper lines. Because one of the advantages of doing plated contacts is you tend to be able to make them a lot narrower than if you're trying to screen the metal onto the surface. Screening is very simple, low cost, it's a great, reliable process, but it is a challenge to make the metal lines really narrow. Whereas with a plated technology, all you need to do is pattern your dielectric, and as narrow as you can pattern your dielectric, you can just plate to the exposed region and very simply produce a metal contact of whatever width you want. And patterning the dielectrics is very easy these days. You can use lasers to do it, you can use inkjet technology, there's a range of approaches that you can use. And so here you see a couple of photos. This is a cross-section of a metal line. In this case, it's about 25 microns wide. In comparison, the screen-printed metal lines are typically 80 microns wide. So a big difference in how wide they are and therefore how much light they shade. And that's part of the reason why this looks so dark, except for the interconnect wires. This is very dark compared to this, where you can clearly see the screen-printed silver lines. Okay, with regard to efficiency, I've already talked about the expected evolution in efficiencies for P-type material versus N-type material. This is simply showing it in graphical form. So I won't go into more detail on this now. It's all on these view graphs. I'll make all these available to everybody who would like copies in the future for those that would like to study it more closely. Okay, that brings us now to trends in encapsulation. I've already mentioned what an important area that is to help bring down the costs. And that's illustrated by these bar graphs at the top here. So going back only 3 years ago, the encapsulation costs are shown here in mauve or purple. Okay, that top section here. The encapsulation costs were only 33% of the cost of making a module. And here was the cell here the wafer here, and here's the polysilicon contribution here. So the making the solar cell, this is the cell processing cost, so you add this plus this plus this, gave the solar cell as very much the dominant cost. Only 3 years later now we see that the encapsulation costs here are equal to the solar cell costs. So we're paying just as much to form the module as to actually make the solar cells that do all the electricity generation. And so we're going to see evolution take place in terms of how the modules are formed and how the encapsulation is done going into the future. Now there's a big challenge for thin films. I've been giving talks like this for the last 30 years. And every time I give a talk, I talk about the challenge for thin films. And I keep having to include it in my talks, because if I don't, someone in the audience always says, but aren't thin films going to take over in a few years? Because the industry has always thought that thin films would take over in the near future. When I set up Australia's first solar cell production line in 1980, 1981, I was actually told that what I was doing was a waste of time because the line would be redundant within 5 years because thin films would have taken over. And the thin film technologies I was talking about, amorphous silicon, copper indium diselenide were the main two at that time, and then a little while later, cadmium telluride. Now, if you talk to people now, 30 years later, some people are still saying, yeah, but thin films are soon going to take over. And you say to them, yeah, and what are the technologies going to be? They'll say, well, amorphous silicon, cadmium telluride, copper indium diselenide. Right? Now, all three technologies have been attempted to be commercialised many times over the last 30 years. Every time it's failed. Right? Usually, it's failed because of durability problems. So a product's produced, it's turned out to be unreliable in its output, unstable, they degrade fairly quickly, they don't survive in the field. I mean, a good example, copper indium diselenide, which is still talked about as being a very viable technology. A lot of people don't remember that in the late 1980s, the world's biggest solar cell manufacturer at the time, they were 4 times the size of any other manufacturer. That was Arco Solar. A couple of people here are old enough to remember, like Dave. Sorry, Dave. A couple of us remember Arco actually shut down all their silicon solar cell manufacturing and turned to copper indium diselenide for all their production because that was the way they believed the future had to go. They started producing their product, they sold a lot, then they started getting lots of warranty claims, so then they had to stop the manufacturing while they sorted out the problems. They worked for 2 years trying to solve the durability problems because modules were failing in the field. They couldn't solve the problems. Eventually they recalled all the product. Eventually they restarted all their crystalline silicon manufacturing and just scrapped the thin film. Okay, now I can give you many examples like that of other companies that have gone into manufacturing. You know, amorphous silicon, there's been quite a few companies that have gone into manufacturing of amorphous silicon, even BP with amorphous silicon with their Apollo, wasn't it? Apollo module. And they had all sorts of yield problems with that and efficiency problems, stability problems. That ended up being canned as a viable technology. Many people forget that BP was also the world leader in cadmium telluride. And that was, I believe, a technology that seemed to be looking very good in the lab. In that case, BP stopped manufacturing. I think that was more because they were worried about the toxicity of the material. Is that right, Dave? Was that the main reason they stopped?
That was the external reason given.
That was the external reason given. Isn't he very subtle? Okay.
Manufacturability again.
Manufacturability, again, a problem. There's many examples of people that keep trying to commercialise thin films. Look, hopefully one day it will happen because it does offer the potential to further bring down the cost. But they're really struggling for a range of reasons. Efficiencies are still too low. Okay, the biggest thin film manufacturer at the moment is First Solar. They're one of the 5 biggest in the world, making cadmium telluride. Okay, I don't like having cadmium on my roof. Some people maybe don't mind it. I don't like it for that reason. Tellurium, it's one of the scarcest elements, and yet they're dependent on that for the solar cells. So it's hard to see how it's ever going to be a cheap enough product to be really widespread in its use. Efficiencies, quite low compared to crystalline silicon. Durability, very questionable. There's been some recent publications at the conference I was just at showing that all the cadmium telluride modules are degrading at least double the rate compared to crystalline silicon. There's a lot of durability concerns. Even First Solar's made some announcements about increased warranty provisions for increased claims on warranties because of modules that were failing in the field. So the point is, there's no thin film technology that's ever been manufactured in large scale that's been out in the field for 10 years successfully. Okay, now hopefully it will happen at some stage. It hasn't happened yet. And so when people say to me, well, isn't it just around the corner that thin films will take over? I mean, it's just not realistic. It certainly won't be within the next 10 years that thin films become the dominant technology. But hopefully at some stage in the future it will happen. Okay. So looking at the high efficiency side of things, everybody wants to move more and more to high efficiency. We can look at the 4 highest efficiency technologies around the world. One's from Australia, this one's from Germany, this one's from Japan, this one's from America. So scattered around the place, all the different countries are making their valuable contributions. This is the world record holder from UNSW with 25% efficiency. But you'll notice there's not a huge difference. In fact, this technology, no, not this one. The Sanyo technology has actually jumped ahead of Stanford University. Now, Stanford University is the sun power technology. The team from Stanford started the sun power as a company and have done a very, very good job commercialising that technology. But Sanyo, with their HIT cell, they've actually jumped up to 24.7. So they're actually closing in on us now in terms of holding the world record. That technology is not a cheap one. It's had a lot of challenges in production, a lot of variability. So although they can make their very best cells of very high efficiency, it's hard to repeatably get that sort of performance level in production. So their average production efficiencies are below 20%. Very big difference. And one of the big challenges there is it's a technology where you've got a silicon wafer still, but they use amorphous silicon to passivate the top surface. And there's no doubt that Sanyo has done a brilliant job passivating the surfaces with their amorphous silicon. They do way better than any other technology is able to do at passivating the surfaces. But the trouble is, having an amorphous silicon thin layer on your top surface introduces some big challenges. Because if you get that layer just a little bit too thin, your surface passivation deteriorates badly. If you make it just a little bit too thick, it becomes very absorbing, and a lot of the light doesn't get through to the silicon to be able to generate the electricity. So it's really critical. And you're only talking about a monolayer or 2 of atoms to go from being too thin to too thick. So it's a challenging technology to get right in large-scale manufacturing. Sanyo have been working at this for decades with this technology, and they're still struggling to get above 20% average efficiency. But it is a technology that you'll probably see a lot more of in the coming years because all the patents from Sanyo have recently run out. So you have some very good companies like Rothenrau looking at commercialising that type of HIT cell technology. So you will see production lines being made available very soon based on that technology, which will use N-type wafers that will probably help push average efficiencies higher. So back to the big question, is it going to be N-type or is it going to be P-type that dominates in the future? Well, I think it's clear it's going to be P-type that dominates overall, but what will dominate in terms of highest efficiencies? Here you have a technology, this is P-type, this is N-type, this is N-type. So there's a bit of a battle there, and it's very much unknown as to which direction it will go. I actually personally think P-type is probably the way to go even for the high efficiency sort of cell technologies. There are others that will disagree, that will say no, N-type is the way to go. So it will be very interesting to see the way that it evolves with time. But there's also a big difference between doing these in the lab and actually coming up with a technology that can be mass produced with commercial tools in a commercial environment. And so the next slide here just gives a bit of a summary of technologies that have gone into mass manufacturing over the last 20 years. And you'll notice they come from all around the world. Australia fares reasonably prominently with technologies from UNSW here that have been successfully commercialised. But most of it has been by the Chinese, and they have done, as I mentioned before, a very good job at identifying the technologies, such as Yingli chose the ECN technology from the Netherlands, and they call that their Panda technology. They've done very well with that in mass manufacturing commercially. JA Solar used the Innovolite technology from the United States. Suntech used the Pluto technology from UNSW here. So, you know, you can go through all these different examples. But one thing's for sure, and that is that the Chinese really have done a very good job at turning a lot of these laboratory type technologies into very good large-scale mass manufacturing technologies of high throughput, high yield, and low cost. Okay, just to finish off with, one of the very interesting ongoing trends for the industry is that we start finding more and more people from UNSW in senior management positions of big companies around the world. In fact, it's got to the stage now where if you look at 8 of China's 10 largest cell manufacturers, keep in mind that most of the big companies worldwide are in China. So 8 of their 10 largest have UNSW students as either CTOs, vice presidents of technology, or CEOs of those companies. And this just gives you a list of those people, and all the asterisks represent current positions. Those without the asterisk represents former students of ours that have formerly had positions in those respective companies. And all in all, we have 22 of our former students, either as CTOs or vice presidents of technology worldwide in solar cell manufacturing companies. Oh yeah, there's one last slide that I've got here to do with the balance of system costs. Okay, they need to be brought down. Making the modules, we've talked about we need to bring down the encapsulation costs, but once you've got the module made, the module is such a small part of putting in a system cost. In the US, it's only 20%. So 80% of your costs are balance of system costs. And some of the dominant balance of system costs include things that are shown here, like the inverter is shown as the bottom bluish region. The purple region here is all the wiring. The light green region is all the mounting. And then the top pinky sort of region is the ground preparation and requirement for it. And you'll notice that the predictions over the years are for the balance of system costs to come down, but probably a bit disappointingly slow. Like in Europe they've already done a pretty good job at bringing down a lot of the balance of system costs, so that on a per watt basis in US dollars, they're down to about 57 cents per watt at system level for these particular parts of the BOS costs. That's expected to come down, but not hugely, to about 46 cents per watt by 10 years from now. US are doing much worse than the Europeans. They're very relatively inefficient. There's a lot of red tape about putting in systems in the US. They have a lot more improvement to be made. So they're expected to come down from the present dollar, right? Dollar compared to 57 cents in Europe. Dollar down to about 64 cents over the next 10 years. And Asia's kind of, they're a lower cost one there. They're already doing pretty well, 47 cents a watt, expected to come down to about 40 cents per watt. And you'll see the areas where the improvements are mainly going to be made. And you'll see that the mounting, this light green area, is where you'll get the biggest improvements in the US, also in Asia, and also in Europe. Okay, so I think that was my last slide. Thank you for your attention.
So, thank you, Stuart. We've probably got time for a few quick questions.
Okay, I've got one very quick one while everyone else thinks. Why are manufacturers obsessed with calling their modules components?
Well, maybe we have to ask Dave that, because I think BP started it, right? BP licensed our technology from here. We just called it something simple like buried contact, right? Because we formed grooves in the top surface, buried the metal, very simple, buried contact. BP came up with the Saturn technology, you know, dealing with the planets. So I think Dave was there at BP managing all their technology development. So Dave, tell us why.
Well, that's true. And BP, whenever they had a project stream, would settle on a theme. And in our case, in solar energy, the theme was the planets. And I think I can say that when Suntech took a technology that BP hadn't, rather than calling it Uranus, which I think was the next thing, they called it Pluto.
Pluto.
Yeah.
Yeah.
Sensible questions there.
You talked about plating and therefore copper as the main conductor in plating, but you said it will not work for screen printing. Now I understand that copper cannot be in direct contact either with the silicon or with the EDA because it will contaminate both. Yeah. But has anyone ever looked at screen printing a barrier layer and then screen printing copper?
There's actually been a lot of work done on the screen printing of copper. So when you go to the conferences, you can always look around and find some papers of people that have developed copper pastes for screen printing, and you find results. And yeah, sometimes they'll use some sorts of barrier layers. I mean, if you've got a barrier layer, you then have the challenge that you have to align your copper to it. And the technology for doing that is getting better and better, but it does introduce yield challenges. You only have to miss in one little tiny area. The copper contacts your silicon, the copper goes into the silicon, damages your junction, damages your wafer, etc. So it's a challenge, but the other challenge is that those that have been working on the paste have really struggled to get good conductivity in paste form. They haven't been able to get, so with silver, if you go back 30 years, Dave, when we were at Brookvale there manufacturing the solar cells, you'll remember that our paste at that time had a resistivity 3 times higher pure silver, right? Now DuPont's done a lot of good work to bring that down so that the resistivity of the screen printed silver now is not much higher than pure silver. In copper, there's still a factor of 10 higher than the conductivity of copper. And there are people working at trying to bring that down. Maybe it just needs the equivalent of DuPont to be able to do that, but that's a problem area for them as well.
Is that because it oxidises during the process?
I'm not sure why. Alison might understand.
The main problem is oxidation.
Yeah, which in silver is not a problem.
Yeah. No,
but in copper is.
Silver oxide's conductive anyway, and it's less reactive. So
there is a lot of work happening on it for heterojunction cells though, on copper, which is low temperature contacts and has TCO as a barrier layer.
Right.
So doing quite a few.
Because you would think the cost driver would be immense to be able to sort out.
Absolutely. Yep.
Any other questions? Okay, well, we might close up now. Just thank you, Stuart, for coming along. For those of you who perhaps don't appreciate this, Stuart has a calendar that would give most people a bit of a migraine. So we really do appreciate you coming and giving us this time. I think it's a really good way of putting everything that these guys are working in course in context. So thank you very much.